All right, it's 2:30, so let's get started. I actually have a laser pointer today, so that'll make it easier. So what I'd like to do today is probably finish off the discussion of oscillation that we're going to need for this class. And just so you know, like on Wednesday, the plan is to begin to talk about gravity a little bit. Orbits, that kind of stuff. But today we're going to keep doing oscillations. So the first thing that I want to do is return to the thing I did right toward the end of the class last time, which is a discussion of the simplest pendulum. Okay? So a pendulum is a simple way of getting simple harmonic motion. That is to say, back and forth motion. Let me get a working marker. Okay. So here's the setup. Here's a vertical axis. Here is some rope. And let's say there's a weight hanging off the rope. I drew this last time. I'm going to draw it again. Okay? So the weight on the end of the rope is M. Okay. So now let's call this angle theta. Okay. So what do we know about the situation? So there is going to be a force due to gravity, right? And there's going to be a force from the tension in the rope, pulling up like that. And the torque due to the tension is going to be 0, and the torque due to gravity, well, it won't be 0, okay? So that means that there's going to be some acceleration. So there will be a net torque, which is equal to the torque due to gravity, which has to be equal to the moment of inertia times the angular acceleration. So just to remind you, so why did I say that the torque due to the tension is 0? It's because the tension is just pulling in towards the axis here. So everything is rotating around this point, so I might as well say that's the axis. And a force towards an axis or directly away from an axis does not produce rotation, it doesn't produce torque. But gravity is not directly along the axis, and so it should produce torque. So now there's a very important thing. We can figure out the magnitude of the torque due to gravity. I'll review how that goes in a second. But the question is, what should we think about when we talk about its sign? And the thing that I want to emphasize here is a bit of physics, not mathematics. Let me see if I can get a marker that actually writes in darker ink. Okay. There we go. Alpha needs to be negative. Okay? So what is alpha? Alpha is how does the speed or velocity of this little thing change. And the thing is, if it's going up, it has to be slowing down, right? Does that make sense? If you have a pendulum and the pendulum is going up, theta is increasing, the pendulum has to slow down. Slowing down means that the acceleration is negative. Here we're talking in terms of angular acceleration. So alpha had better come out to be negative. Okay. Now what does alpha actually look like? So alpha is d2 theta dt squared, right? That's the derivative of the question. And so what that means is that this thing right here needs to be negative. That is a physics thing about what we think is actually supposed to be happening here. That is, a pendulum that's going up has to slow down. Okay, so now, what is the moment of inertia? I. If the rope that is attached to the mass is massless, or basically very light, then this is ml squared, where the length of this rope is L. And finally, the magnitude of the torque due to gravity, I don't remember what it is. Let's see, it's mg times L times sine of some angle. So let's try to work it out. So let's see. So we need this angle. This is the angle between G and the vector that takes us to here. You could call it the L vector. Okay, so if this is theta, this is 90 minus theta, this is 90. So the angle that we actually want, I went through this last time, my apologies for going through it again, is 180 minus theta. So there we go. Now to figure out what this is, I have to draw a picture. So if this is theta, then this angle is 180 minus theta, right? You go to 180 and you go back a little bit. And the sine is here. So the sine is there. So this is what sine is. So we get mgl sine theta. And finally, we recover the equation that I was finishing with last time, which is ml squared. The second derivative of the angle has to be equal to the torque. mgl sine theta. And now watch out, this thing is positive, this thing so far is positive, but we want the acceleration, which is this thing. This is alpha. We want that to be negative. We said that earlier, because the thing needs to slow down. So we have to stick a minus in there to get the physics right. So finally, if I cancel some stuff out, I'll get this. Okay. So last time I tried to explain this, I somehow wasn't like super sharp about saying the reasoning that leads to the minus sign. So I wanted to clean it up today. Before I go on, any questions about this? This is all going to be in the notes that are available online. But do you have any questions for now? Okay. Same question I asked before. So now, I think I said this at the end last time, but it was starting to go way too fast. All we have to do now to understand how the pendulum swings back and forth is to solve this kind of equation. But this is easier said than done. So the key idea for understanding what's happening is the following. If we make a picture, okay, here is theta, here is sine of theta. Let's look at what this actually looks like. Okay, this is the origin, this is 0. So sine of theta starts at 0 and goes up, and then comes back down, and then goes back up. You'll buy that? It keeps going, it wiggles back and forth. So let's see, where does all this stuff happen? So this point is pi, and this point is 2 pi. I don't know if you buy that. Do you buy that? Does that ring a bell? So if I draw a unit circle, and I draw a little triangle on the unit circle, and call this angle theta, and this is 1, this thing right here is sine of theta. Okay, so if you're at 0, this part is 0. That's here. If you go up there, oh, I forgot, this is in radians. I'm using radians. If you go all the way up there, that's like 90 degrees, pi over 2 radians, then the side length of the triangle in the vertical direction, well, it's not really a triangle anymore, but the side length is 1. This is 1. You keep going down over here to pi radians, also known as 180 degrees. You should get 0. You keep going. So why am I drawing this? I'm drawing this for the following silly reason. Let's ask, what happens near this point? So this is the 0 point. Near this point, the function looks like the function theta. That is to say, you can approximate this wiggly thing if you're close to there by a straight line. That is kind of visually clear. Does that make any sense? So basically I'm saying anything that's like changing and wiggling in a complicated way near some particular point, it always looks linear. That's all. So that means that while in general this is very complicated, where do I write this? Maybe here. If theta in magnitude is very, very small, small compared to what? Well, maybe small compared to that point, right? So this is pi over 2. So pi over 2, or if you want to say 90 degrees, if you're pretty far from 90 degrees, if the angle is like 3 degrees, okay? You pick your choice of units for how you measure degrees. Then sine of theta to a very good approximation is equal to theta. I didn't draw this picture last time and I should have. So if that's true, then the equation that looks pretty difficult over there becomes that. Because you can replace sine of theta with theta. And now that we've done that, we can write another equation just out of thin air that we looked at before for the mass attached to a spring, which looked like that. Let's see. We've looked at this equation before, and here we knew that the solution for x of t like we got this equation earlier when we thought about a mass attached to a spring. We got this equation. And I tried to convince you that the solution of this equation was a thing wiggling back and forth described by this function. So if you believe that, then this equation looks the same except you replace x with theta. And you replace k over m with g over l. So it means that here the solution should be theta as a function of t. That should be the solution. So if you believe one of the statements there, you should believe the other one. Okay, so I'll skip these slides. So what I'm really doing is something that you may have briefly seen in a calculus class, or possibly not, which is that the sine function can be approximated as a polynomial, which is the theta that I wrote down, but then there are small corrections to it, like minus 1/6 times theta cubed plus 1 over something big times theta to the 5 and so on. But you know, all of these extra terms with the theta cubed and the theta to the 5 and whatever, they're all very small and theta is small, so you can just do the replacement that I said. This is called Taylor's theorem. It's probably the deepest thing in calculus 1 or calculus 2. The math people don't usually spend that much time on it, but it's pretty important. Okay. This is the picture, okay, that I just drew on the board. This is for the sine function. Here is the same thing for the cosine function. It approaches a constant when x is, or in that case, the angle is small, but then it deviates a little bit like a parabola. So both sine and cosine have these kinds of expansions around the origin. Okay, this is very deadly material, I can tell. Okay. The punchline, again, is that this makes it much easier. So a pendulum which starts here and goes down and comes back up, okay, that's very difficult to solve. It can be done, but it's just very hard mathematically. But a pendulum that goes from here to here, and like that, a tiny bit, pretty easy to work with, as long as it doesn't go too high up. Yes?
How do you determine something is not too high up?
Good. How do you determine, that's a great question. The question was, how do you determine if something is not too high up? So for this to work, I needed to be able to replace this thing with theta. That's what I need. Okay, so when is that legitimate? Okay. Well, if I try it when theta is around pi, it's a very bad approximation. Because if theta is equal to pi, right, then the function, this thing just worked, and worked better than any other marker. What is happening? Let's compare the two functions. We have the function theta and the function sine of theta, and we plug into both of them. We plug into pi. And one of the functions gives us pi, the other one gives us 0. Right? This one gives us 0, this one gives us pi. So they're like very different from each other. On the other hand, if theta is 0.01 pi or something, okay, we take this thing, we plug it into here, or into here, we're going to get very similar numbers, because look at this picture. Right, so basically, as long as you're not too far away from the origin, it should be well described by a linear function. So my question is, what does not too far away mean? That's really your question. Well, basically, not too far away means you stay away from any, you don't get any close to this point. So where does that occur? It occurs at pi over 2. So the condition is theta should be much less than pi over 2, or another way of saying it is much less than 90 degrees. So much less than 90 degrees. So what does it mean to say much less than 90 degrees? I mean, if you want it to be a really solid approximation, a tenth of that is decent. Okay? So 10 degrees. If you start 10 degrees off from the vertical, it's pretty good. 30 degrees, very questionable. 50 degrees, really, really questionable. Anywhere past that, like I wouldn't trust it. 5 degrees, oh, wonderful. You know? So that's the idea. So the question is, when does the approximation that I use make sense? And that's as long as you stay away from 90 degrees. Okay. Good. So the thing that maybe is worth pointing out here is that the answer that we just got depends on which planet you're on. So it depends on the acceleration of gravity, namely g, and it depends on the length of the pendulum, like how long is the thing, but nothing else. It doesn't depend on the mass that you stick on the end of the pendulum. Okay. Of course, we only considered a very simple pendulum, and it's natural to ask, well, you know, what if it's more complicated? But before we do the more complicated thing, since you dragged yourself here on such a rainy day, I thought I should try to give you a chime-in question. Get you some free points, basically. Please tell me if the question is not visible. I just activated it. If you don't see it, something went wrong. Okay. So I'm going to walk through this so that you don't necessarily have to do that much in your heads here. So imagine we have two pendula, or pendulums, I'm not quite sure what the right word is, and one of them is 4 times as long as the other. So how are their periods related? Okay, so the information that, let's say you're given on some formula sheet, if this was a multiple choice question on a final exam, that's a hint. This would be a legitimate multiple choice question. Would be that the period is 2 pi over the angular frequency, and the angular frequency is the square root of g over L. Okay. So let me show you how to think about this problem. So the period for one of them is 2 pi over omega, which is that, which I can also write as that. The period for the other one okay. So that's very general. I have two pendulums, they have two lengths. Okay, but now we were told something about the lengths. So for the long pendulum, let's say that's L2. This is the long one. Its length is 4 times as long as the other one. And then we take a ratio of these two things. So we take T2 over T1. And let's see. The 2 pi's are the same in both places. The g's are the same in both places. So all that we're going to have to deal with is L2 over L1. So that's going to give us 2. So I desperately hope this is what okay, good. It is what I thought earlier. Any questions about this? Does it make sense? Do you have questions about the reasoning? So, if it's clear, that's wonderful. If it's not, please make sure you understand this by the final exam. Not saying this particular question will be on the final, but you shouldn't be shocked if it is, and you should understand how to do this kind of thing. To be clear, assuming that somebody handed you this formula and that formula, which you'll get on the formula sheet. Okay. So what about actual pendulums, right? Like, real life pendulums are rarely just a mass on a very long string, which is basically weightless. Like a real life thing that swings back and forth will look, something like this thing, right? So there'll be some kind of complicated shape. It's got some center of mass in some random place, and it's swinging because it's being held somewhere, and it's swinging back and forth. That's what a real pendulum looks like. So how do they swing? Believe it or not, it's actually, with everything that you know by now, it's actually a pretty straightforward thing to understand. So let's see how it works, as long as you don't panic. If you panic, it's very hard. But if you don't panic, it's not so bad. See, somebody has to tell you a little bit about the object. So, let me draw it here. So here is the object. Okay? Here's the axis. And here's the center of mass. Okay? It's just somewhere else on the object. So somebody has to hand you the moment of inertia for the object around its center of mass. Without that, you don't really know what to do. But suppose somebody tells you that information. That is to say, what would happen if you put the axis there? Well, if you put the axis there, first of all, if this is also the axis, the torque due to gravity would be straight down, and it wouldn't give you any torque, right? The force of gravity would be down, and it would be like applied at the axis, so nothing would happen. The thing wouldn't even swing. So the interesting thing happens if the axis is in a different place. The axis is there, and this is the center of mass. Now, you have a radius vector and a force of gravity, and gravity really produces a torque, and so the whole thing will swing back and forth. And so, again, suppose somebody told you what this is. So this is given. Okay. Then, what you really need is the actual moment of inertia for the axis that you're actually using, which is I center of mass plus m r squared, where r is the distance from here to here. This is just a parallel axis theorem for which a formula will again appear on the formula sheet. It's literally that formula. Okay. But if you think that way, then I'll skip to the next slide just so you can sort of stay along with me. It looks a bit busy, but I'm going to try to make it simpler. All that's happening is you have a torque due to gravity, which in magnitude is the same as it was before. It's mg, well, r in this case, if this is the distance here, times sine of some angle theta, where the angle theta is now this angle. Okay, the net torque in magnitude is just the torque due to gravity, but also the net torque has to be equal to I times alpha. But it's the actual value of the moment of inertia that's relevant here. It's just F equals ma, but for angular quantities. So, just as before, we say to ourselves, all right, well, I can just relate these things to each other, and remember, have to keep around the minus sign, because if it goes up, if it's going up, then it's got to be slowing down. So the angular acceleration has to be negative if it's here. So then, I actual, for which we have a formula right here, in terms of something that's given to us, times the second derivative of the angular position, that is to say the angular acceleration, is equal to mgl sine theta, but with a minus sign, for the reasons that I said a minute ago. Okay. So basically, we are set. So here I just divided both sides by the actual moment of inertia and plugged in the formula for it in terms of the information that we have, which is somebody told us the moment of inertia around the center of mass. Somebody told us the mass of the pendulum, and there we go. And this letter m is intended to be the same the entire time. It's the mass of the pendulum. Do you see how I did that? Do you have any questions? Like, basically all I did is I took the information that I was given for the moment of inertia, translated it to what I would actually need to set up the problem. After that, everything was exactly the same as for a point mass pendulum. And then simplify slightly, you get that expression. So in this expression, it's not obvious that the answer is independent of m. In fact, it looks like it obviously does depend on m. Right? There's an m here, there's an m there. So there's something very funny that you can show. So very generally, the moment of inertia of some object around the center of mass is some number times its mass times the size of the object squared. So this number here depends on shape and mass distribution. So it depends on the details of the object. Somebody has to work very hard to calculate it for you to measure it. But you can always write this thing in that way, always. So, but that means that I can rewrite this stuff in yet another way. Okay, I did something very bad here. None of you yelled at me, so it means that I've completely lost all of you. I wrote MGR here. Nobody complained yet, as far as I can tell, that I wrote MGL over there and over there. So it should have been R. My apologies. So the point of this exercise is that the m's cancel out. This m cancels that m and that m. Sorry, I'm trying to get this straight. Okay, so this is how a real pendulum swings. This is the equation that tells us how it swings. And so what appears in this equation? It's again, the acceleration of gravity, namely which planet are you on? R, how long is the thing that's swinging? And then 1 plus some constant, and that constant is determined by the exact details of the shape, and like what does it look like geometrically, and where is all the mass, and all of those horrible complicated details you need to use calculus 3 to figure out. But it's pretty simple. And finally, the angular frequency is the square root of this thing. So when I say it's simple, I mean it's simple compared to what you might have thought, which is that an arbitrary pendulum might have an equation that it follows that's very complicated. But it isn't very complicated. It looks just like the other equations that we've been writing, except that the prefactor of the sign is changing slightly. So if the angle is not too large compared to 90 degrees, if it's small compared to 90 degrees, we go back over here. We notice that you can replace sine theta by theta, and you reach an equation that looks like this, where this guy gets replaced with G over L 1 plus C, and this thing gets replaced by the thing that I just wrote on the other side of the board, just by replacement. That's why I wrote the formula for the angular frequency that I wrote a minute ago.
I have a question.
Yes?
Why did you drop the sine of theta for when you took the square root at the very end?
Here?
Yeah, like you had sine of theta, right? So
Perfect.
there you go.
Why did I drop the sine of theta? So what I'm doing is I'm saying, this is the equation I have to solve. It's how do I put this? It's just as hard, but not any harder at least, than the equation that I got with a standard pendulum, which was very simple, where the mass is all just at the end. It looks exactly the same except this extra factor downstairs. So to actually solve this equation, to have any chance of solving it, I need to replace sine of theta with theta, which I could get away with as long as the angle's not too big. Okay, once I do that, where am I? Yeah, you would reach this equation, except instead of G over L, you'd have G over L, oops, that was a typo. You would get G over R 1 plus C. To match notation over there. Okay? And then over here, you would get this. So then you reason by analogy. Other questions? Okay. Man, oscillations are deadly compared to the usual things that we've talked about. Okay, we're almost done with them in case you're wondering. This is just to say that everything that I've been talking about is buried in the slides. I'll update the PDFs and PowerPoint slides on Canvas shortly. So this is very abstract for the moment, so why don't we try to figure out like a simple case, okay? Just do an example. Okay, so let's say I have a stick. It's attached to something over there, this is the axis, and it swings back and forth. And suppose that the angle here is guaranteed to be small, so I don't move the stick too much before I let it go. So then, what is the oscillation frequency? So, to be clear, this is something that in principle could be asked of you on the final exam. So, to answer this question, what you would need is some information about the center of mass moment of inertia for a stick, which would also have to be given to you. That is 1/12 ml squared. So that would be around this point. Okay. So the actual moment of inertia that you need is the moment of inertia around the end so that's L, this is L over 2 squared. And I'm going to cut to the punchline here, which is that this is a third ml squared. Not because it doesn't take a bit of work to see that, but because we've done it before many times. So if you take that thing, plug it there, simplify, you will get that. Okay. So, let's see, this is what we need to deal with now. Okay, so we have okay, I just plugged in everything into the equation that I had over there. Simplifying it slightly, the m's cancel, and I get 3g over L with a minus sine theta. So if theta is very small, then I can approximate sine of theta with theta. So I get minus 3g over L theta. And this thing is the angular frequency squared. So the angular frequency is square root of g over L times the square root of 3. Assuming I haven't screwed up the arithmetic. Did I scrub the arithmetic? Interesting. Well, my answer right now disagrees with the answer of me from last night. So what was I doing? Let's see. Oh yeah, I completely forgot to actually write the torque equation. That was my fatal error. Okay, so you got to take into account that gravity pulls from this point. So it pulls from the point L over 2. I forgot that. That was my error just now. So there was a factor of 2 here. So there is a factor of 2 there, and a factor of 2 there, and a factor of 2 there, and then it actually agrees. So if I had actually carefully set up the torque equation again, I would have got it right. But I failed to do that, and so I almost got it wrong. Okay. Also, by the way, in case you're worried, if you were to get a question like this on an exam, I would try to make sure that it's broken up into several parts and you are guided into how to do it. So you'd be asked, what is the torque due to gravity? What is the moment of inertia of this object? Okay, what is the relationship between these quantities? Okay, well, how can you simplify this if the angle is small? It will be broken up a little bit. Okay. So, before I forget, I can't quite remember. I think on the homework assignment there might be some question about something called a torsion pendulum. So just in case, I want to mention, such things exist. The way it works is that you take a solid object, like this pen, and you hold one end of it fixed and you twist the other end. Now, this is obviously hard to do with a pen. But if you had a very, very long wire, then you can imagine this would work. Okay, the wires can be twisted a little bit. But of course, if you let go, the wire tends to go back. And it will go back and forth, back and forth. Solid objects want to maintain their shape, right? So, for small twists, what you need to know is that the restoring torque in a torsion pendulum is just proportional to the angle. And so these things follow simple harmonic motion. That's all you need to know. So let me not say more. Okay, I don't think you need to know more for the homework. For the spring constant, for this kind of motion, just replace it by the torsion constant. And somebody will give you the torsion constant. It's a property of the material. Okay. So the last thing that I want to do today is to talk about something more in the real world, which is what if you have an object that can move back and forth, but you have to worry about air resistance. After all, air is a thing, air resistance is a thing. Like, what happens if you take it into account? Okay, so the first thing you need to understand for that is like, well, how does air resistance depend on the speed of an object? Because if you go faster, the air pushes more, right? So the thing that we need to take from some experiments or something is that unless you're talking about supersonic motion, where things get very complicated, for like normal motion, like if you're just running or if you have a sail on the ocean or something, the air friction force is just proportional to velocity, the first power of velocity. So, okay, so how do you take this into account? Well, okay, it's nasty, okay? So what happens is, first, you have the acceleration is given by Hooke's law, right? So this is the thing that says that if you pull a spring, it pulls back. That's the thing we had before. And then there's something that is involving the velocity over here. And the parameter b depends on the shape of your object, the density of the air, and so on. dx dt is just the velocity. That's the air resistance term. And so now, what you have to do is do the horrifying thing of solving this equation, which, would be horrifying, but you solve it by guessing, yet again. So what should it do, okay? So look, if you have something that's wiggling, and there's air resistance, as the thing is moving, it's always slowing down, right? So what ought to happen is as it wiggles less and less. So let's draw a picture of that. So here's time, here's the position. So you start out over here, you take your spring, you stretch it, and then you let go. And then it goes back and forth. So first it goes back and forth like this, but then it starts slowing down. So it doesn't go back and forth as much. And it doesn't go back and forth as much, and it keeps slowing down, and slowing down, and slowing down, and stops. Does that make any sense? Like that's what ought to happen. So now the way I just drew this, it suddenly goes further than you started it, so that ain't gonna happen, but okay. So now we can ask ourselves, okay, well, what does this look like? Well, clearly there's some kind of wiggling. So I don't know, let's say there's some omega times t. So there's some wiggling going on. But also, the wiggling is getting squeezed. So how is it getting squeezed? Well, the way I drew it, it's not obvious, okay, but you can play around, and it's a reasonable guess that you can then check that the way it's getting squeezed is like that. So it's just exponentially squeezed. Eventually stops. So this is just a guess. There's no reason for this to be correct until you just write down your guess, which is a wiggly thing times a thing that's collapsed into zero. You plug this function back into the horrible equation I just flashed for you, which you probably don't want to see again ever in your life. And you demand that the thing you plugged in is a solution and see if it works. And it turns out it works if you choose the constants in this trial function to be some particular special ones. Okay? And so it does exactly what you think. You take a mass on a spring, you wiggle it, you let it go, it wiggles, but then it slows down and stops. That's exactly what this thing is doing, and you can figure out how it's going to stop, how it's going to slow down, and exactly how it's going to wiggle. The actual shape looks something like this. Okay. I think I should end the deadliest lecture of the semester here. Next time, we're going to do a demo, which I think